All right. So, sorry for the late start. I had a coffee mishap, so I was wearing something over this before. So, I have two Great Pyrenees dogs, and so if there's a bunch of hair on this black shirt, I had something over it, so that's why I might look a little bit of a mess. So, we'll kind of pick up where we left off, kind of using those week 5 slides. Today, we're going to be using this MLR week 5 do file. Once we kind of jump into Stata. So one thing I did want to mention, if I come back here to problem set 2 before we get going. So question, I believe it's 11. What I had intended was for you to run a continuous regression where you had married as the dependent variable, and education as your X variable. The way this is phrased, kind of talking about having a college degree, not having a college degree, I can understand how you might have created dummy variables and then ran this regression and interpret those coefficients. That was kind of more of question 12 where I instructed you to create a variable, right? So if I don't tell you to create a variable, generally you just use the variables in the data set or that continuous variable. If you did treat it and created dummy variables, I'll kind of grade that either way, whatever your kind of interpretation of that question was. But if you haven't completed it yet, I would suggest trying to treat that education variable as continuous. You shouldn't have to create any variables for problem 11. Okay. The other thing I'll mention is I think when I uploaded that one of the data sets, I had some variables in there that kind of seem like they might be the answer to different questions, but I update these semester to semester. So I think they're like called difference variables. Don't worry, like the name is like difference this. Don't worry about those. In fact, don't use those because they're likely not the right answer because they were for a different semester. Okay. So don't put any stock into what those values are. I accidentally kind of included those variables in the data set. I never mentioned them, but if you saw them, don't put any stock into what they are. Okay. So this problem set and that second quiz is due when? The end of the day tomorrow. Okay. So I've got a GA who helps me grade these. He'll kind of start, as I talked to him today, he's planning to start this weekend. So you might see those grades start to pop up. I likely won't get to this. Probably not until Monday. I am hoping to get through most of them Monday. So by the time we meet Tuesday, most of those should be graded, or you probably should see those problem sets graded by the time we get into class Tuesday. Okay. Any other kind of logistics stuff before we dive into material here today? Okay. So we're down here last class. We talked about kind of R squared, adjusted R squared. I said we will kind of start doing multiple linear regression today. Okay. So I had someone stop in yesterday and we started to think about when I run these regressions, I'm trying to predict Y using X. If I'm using one variable to predict something, what do you think is probably true about my predictions? They're not going to be very accurate, right? Even when it comes to like your GPA, there's a lot of other factors, right, outside of one variable that would explain what it is. Right? So our R squared, when we run these simple linear regressions, is probably going to be relatively what? Low, right? R squared is the proportion of the variation in Y that we can explain with just our one X variable. We're just using one variable. We're not going to probably be able to explain much of the variation in something, right? So our predictions are going to be pretty bad. So what does that mean about our error term? The difference between the actual Y values and our predicted Y values is going to be pretty large. Right? So how do we solve this issue? Well, luckily, we can do multiple linear regression. And when we try to predict a Y variable, we can actually use as many X variables as we want. So most of the examples today, I'll kind of keep that to like 2 or 3. So we're not kind of getting overwhelmed or overloaded. But think about an example like this, right? If I'm trying to predict crime rates and I just had the number of police officers in that county or that state, whatever level we're looking at. Well, if I don't include other variables, what counties are likely to have a higher number of police officers? Counties with a lot of people or fewer people? A lot of people. So what's going to be true about the number of crimes when there's a county where I have a high number of police officers? It's going to be high. So if I run this simple linear regression, I just use police officers, what's that correlation between the number of officers and the number of crimes? Highly positive, right? The more police officers I have, it's likely larger counties, there's likely going to be more crimes. Now, does that mean hiring more police officers is increasing the crime rate? Well, no, right? We haven't accounted for these other factors that matter a primary one here that I'm kind of thinking about is population. Right? I know that when the population is higher, it's likely that both crimes and the number of officers are going to be higher. So if I don't include this variable, what ends up happening, and we'll go more in depth into this, is that my coefficient starts to pick up not just the effect of the number of officers, but all these other things correlated with the number of officers that I'm not including in my regression. So if I think there's other things that matter, I want to make sure I'm including them in my regression. So once I include population, the interpretation of our coefficient changes a little bit, okay? So I'll kind of foreshadow a little bit, but if this is just the number of officers and the number of crimes, right? How would I usually interpret beta 1? So what's a 1 unit change in my x variable? Having one more. This is the number of police officers. Having one more officer would increase or decrease my predicted crimes, number of crimes by whatever beta 1 is. That interpretation stays the same, but we get to add on a very powerful statement, holding everything else that we include in our regression constant. So now it's like the thought experiment is holding population count constant. So I have 2 counties, same population, but one of them hires one more police officer. What was the change in the number of crimes? That's a lot more powerful of a statement. We're holding constant. We're now comparing apples to apples, right? We're comparing 2 counties with the same population, but one of them has a 1 unit increase in the number of officers. Okay.
It's like this is adding more variables, but those variables are intended to be constants, basically.
Nope. So that's just what's added to our interpretation, right? And I'll have make a little more sense here in a second with another slide. So you can think about it as when I'm trying to predict crime, it's not just holding this constant, because at the same time, I could interpret this coefficient. How would I interpret this coefficient? If this is the number of people in the county, if the number of people in the county goes up by 1, this is the expected change in my y variable, or the number of crimes. But now what do I get to add on to the end of that statement? Holding the number of officers constant. So it's not that I'm holding all these things constant. It's just when I make the interpretation of one variable, it's holding everything else constant. If I was to try to come up with predicted y values here, well, I run this regression, I'll end up with coefficient estimates for each one of these. So if I wanted to know the predicted crime rate of a county that has 50,000 people and, I don't know, 100 police officers, what would I do? Well, from a very simple linear regression, let's just think about, I had to check my phone on that one. So let's think about if I had crime rates, and let's just say I found these hypothetical values for beta 1, right? How would I predict the number of crimes for a county that has 50 police officers? All I would do is what? Plug in that value I want to make the prediction for, right? Plug in the value for my x variable that I want to predict. So my predicted crimes here would be what? 50 plus 25 times 50. The same thing is going to apply when I run a multiple linear regression. So let's say I run this regression. Now I find, I don't know, here's my coefficients, but I can also find the coefficients for this additional added variable, which was population. I do the exact same thing to predict crimes. I can predict the number of crimes for any combination of these 2 variables. So maybe I want to know what's the predicted crime rate. Well, the constant always gets added in, or my intercept. But now for a county that has, I don't know, we'll say 200 police officers and has a population of 40,000. So I come up with my predicted y values the same way. It's just now I have more coefficients and more hypothetical values to plug in for these different variables. But kind of at its core, right, we're doing the exact same thing as what we did with simple linear regressions to come up with those predictions. Okay. Any questions on this idea? I'll use these values, and I have something more theoretical in the slides. But to kind of support the idea of why we now interpret this as all else constant, if I was trying to predict the crime rate instead for a population of 40,000 people, but they had 201 police officers, how would I make that prediction? Well, the intercept would get added in. The coefficient on police officers times the number of police officers now is 201. Plus, I've kept population the same. So what's the difference in my predicted Y value? When I increase the number of police officers by 1, the change in my predicted value is simply that coefficient associated with that variable that went up by 1 unit. Okay? Holding population constant, right? If population was the same value, beta 1 here would represent the increase, in this case, in the number of crimes from a 1 unit change. Okay? So that's why the interpretation is what it is. Now, how do we find these coefficients? Okay, so this is where we're going to gloss over this a little bit because Stata does all the work for us. It's still the exact same thing we were doing with simple linear regression. We want to minimize the sum of these squared errors that we're making. So the difference between the actual and predicted Y's. But now I've got 2 variables that I'm trying to find the coefficient for. So we only had the intercept and we only had 1 variable, beta 0 and beta 1 were all we were trying to find. We said we could take a derivative of our regression equation in respect to kind of both of those things, 2 equations, 2 unknowns. We could then solve for what those coefficients are. If we add in a variable, we now have the intercept coefficient, the coefficient on variable 1, the coefficient on variable 2. So now we need to take a derivative of our regression equation in respect to each one of those 3 things, 3 equations, 3 unknowns we can then solve for. Okay. So in general, the number of variables we include doesn't have to be 3, it could be 4, 5, 6. We would take that many derivatives plus the constant. Then we would have n plus 1 unknowns or equations, n plus 1 unknowns. We could do this math. The math would not be fun, right? It'd be a lot of algebra, right? In fact, what you would end up doing is using linear algebra to then solve for these. So we're not going to have to do any of this by hand. Stata does all the work for us. So behind the scenes, it takes all these derivatives, set these equations, have these 5 equations, 5 unknowns, and then solves for all of what those coefficient values should be. Okay. So just to kind of write out more theoretical when I was giving you some actual numbers here, you can think about my predicted Y values. When X goes up by 1 unit, X1, if I change X1 by 1 unit, but I'm leaving X2 the same, beta 1, well, I'm multiplying by X1, but then I'm also multiplying it by the change in X1, that 1 unit change. So what's the only thing that gets added into my prediction? Well, if this is a 1 unit change, simply beta 1 more time, right? So, if I multiply beta 1 by 50, and I multiply it by 51, beta's been added 50 times, and it's been added 51 times. That difference is just beta 1. Okay? So that's why the interpretation is what it is. It's just like what we were doing before, but we get to add on this powerful statement, which is holding every other variable in our regression equation constant. Okay? So we'll get a lot more practice with this as we look at examples. Excuse me. So I think I chose some different variables here just so we can kind of get some work and compare this to what we've been doing. So, what am I trying to predict here? I think I left this off. So this might make a little bit more sense if I actually tell you what that, Y variable is. Now we could technically do this for a bunch of different variables. But let's say I'm trying to predict wage. And now I've not only included 2 variables, I've included 3. So I included IQ, age, and experience. Okay. So how would I interpret beta 0 now? So how do we interpret intercepts? It's the predicted value of Y, so the predicted wage, if we had a simple linear regression, it was when the X variable was equal to 0. So now what do you think the interpretation becomes? The predicted Y value, how would beta 0 be the only value that we would predict Y to be? Only if all 3 variables were equal to 0. So it's very similar. It's just now instead of 1 variable being equal to 0, it's everything we include in our regression. This is where now the intercept interpretation is very bizarre, right? Because it's very unlikely we see someone with 0 years of age, 0 IQ, 0 years of experience. This was kind of the idea of like the scatter plot. We said it has to intercept somewhere. We now have like this 3-dimensional, actually here are 3 variables. It's like a 4-dimensional thing that we can't even visualize. There's going to be some starting point. Okay? So the interpretation of our intercept or our constant starts to get pretty weird. Now, how would I interpret beta 2? So we said the interpretation of our coefficients is always a 1 unit change in that variable. So what would a 1 unit change in age be? If I am, it's measured in years, if I am 1 year older, the expected wage goes up by, I think this was maybe hourly, so $23 an hour, holding IQ and experience constant. Right? That's a lot more powerful of a statement, right? Because if I don't control for that, what is definitely going to go up? Well, what is likely to go up if I have 1 more year of age? Experienced, right? So I'm now holding constant experience and say, okay, now what's the impact if I have 2 individuals? The thought experiment becomes 2 people with the same IQ. We're holding that constant. They have the same years of experience at this job, but one of them is was 1 year older, right? Has a little more seniority, or I shouldn't say seniority, has a little, is a little bit older in age, right? So that's a lot more powerful of a statement. And then we can interpret these other variables kind of the same way. How would I interpret beta 1 here? So I go down to IQ. If this is hourly wages, how would I predict beta 1? If an individual's IQ goes up by 1 point, the predicted change in their hourly wage is $8.4 an hour, holding age and experience constant. Right? So once again, you can almost think about the real thought experiment with this interpretation is 2 individuals who are the same age, have the same number of years of experience on the job, but one of them is just scored slightly higher on this IQ test. That would be their kind of predicted change in wages. Okay. Now, just like before, I could scale all these variables effects up. So if I know the effect of being 1 year older, how would I find the effect of being 13 years older? Well, I know the effect of 1 year. How would I scale it up to 13? Simply take beta 2 here and multiply it by 13. So we can always go from a 1 unit change to whatever number of units we're interested in. Okay. So hopefully we're seeing some reoccurring themes of what we do with simple linear regression. We just get to add in this additional statement, but it's a powerful statement, right? Especially you can imagine, what if I start to include like not just age, IQ, experience, maybe I include their education. Maybe I start to include what state they live in. Maybe I start to include their parental income, right? Their parents' income bracket. I can start to include all these additional variables. Now, any one of my interpretations is a change in that X variable holding everything else in my regression constant. You now get to some pretty powerful statements, right? I'm getting a lot more apples to apples comparisons, okay? So we kind of already went through this, right? I gave you some hypothetical values here, but let's say I wanted to predict the wage of someone who's 105 IQ, 10 years of experience, and 45 years old. What would I do here? Well, what always is going to get added into my prediction? It's the thing that is added in every single time. It is the constant or the intercept, right? So all I would do is I would have this simple linear regression equation written out. So maybe to kind of help you out here, if I'm trying to predict wage, that would be these estimates that we have for every single variable. Let's see if I can get the order correct. I think this was the order that it was in the slides here. So I'm now thinking about if I wanted to come up with a predicted wage for someone who has a 105 IQ, their age is 45, they have 10 years of experience. All I would do is look at that regression output and start to plug in all the estimates that I had for these coefficients. Now, this is where be careful. Some coefficients will be negative, right? The relationship between experience and wage here starts to get negative. This is kind of weird, right? Because what is experience picking up? It will pick up the impact of experience on wages, but anything else I left out of my regression, it could be picking up that effect as well, right? Anything I leave out is going to cause what we call bias in our estimates. Right? This is the idea. So maybe what's something that would increase with experience that could hurt your wages. So right now is a very good relevant time, right? If I have 10 years of experience on a job, what is a skill or something, a tool that I might not know how to use? AI. So even though I have one more year of experience, that's likely to be correlated with I haven't been in school, I've been working, I don't have this new acquired skill. What would the effect of having AI be? Probably increase wages. So if I don't have that skill, what's likely to happen? It's going to decrease my wage. Experience is kind of picking that up. Right? So we'll talk a little bit more through kind of why that is and how we determine what that bias is, but that's why we might get some weird interpretations, right? Because there's likely, just like there was more than one variable that mattered, there's likely more than 3 variables that matter for predicting wage. And we've only included 3 of them, okay? Any questions up to this point? Once again, a lot of this is kind of what we talked about with simple linear regression, just a little bit different. Now, we'll go through this very quickly. Because what happens when it comes to being able to reject our coefficients? Everything's the same, right? We still assume that every coefficient is equal to 0. We always have a two-tailed test. We always compare our test statistics to the critical value or our p-value to alpha, or we can look at those confidence intervals and see, do they include 0? So our rejection decisions, same thing we were doing when we had, simple linear regression, right? So I'll go back a slide just to get some practice with this. Which of these variables could I say have a statistically significant relationship, let's say at the 99% level with wages? Well, to have a statistically significant effect, or to be able to reject the null if the effect is 0, if I want to say this with 99% confidence, my p-value needs to be less than 99% confidence. Alpha would be 0.01. So can I reject the null that IQ has no effect on wages? Yes. Can I reject the null that age has no effect on wages? Yes. Can I reject that experience has no effect on wages? Not even close. So even though I have a negative correlation here, if I can't reject the null that it's equal to 0, what actually is the estimated effect of experience? 0. I can't say it's any different than that, right? Now, I would still interpret it the same way, that having one more year of experience, holding everything else constant, decreases my wages. So I interpret it the same way, but at the typical statistically significant levels, I can't actually say that that effect exists, right? Because I can't reject that null. And then once again, just to reiterate this, if I can reject the null, what value should not be in my confidence interval? 0. Right? I'm rejecting 0. So with 95% confidence, if the true effect is somewhere in this range, if 0 is not one of those values, I can reject that 0 is the true value. So notice when I rejected the null here, 0 wasn't in my confidence interval. When I rejected it here, 0 wasn't in my confidence interval. When I failed to reject, 0 is in my confidence interval, right? It could be one of the true values. Okay. So same rejection decisions and things that we were using before. Okay. Any other questions at this point? And technically, I usually don't add this on when I'm saying it just for the sake of brevity. Technically, we're saying that we reject or fail to reject the null, holding everything else in that regression constant. But since we usually add that in your interpretation, I'm not going to try to trick you with that. That's just kind of always, we're just testing to see, is it different from 0? So, kind of went through this. So we're going to dive a little bit deeper into this idea that when I leave out variables, it's going to cause what we call a bias in my estimates for most coefficients. So here, what we're assuming is 4 things when we run these regressions. And we kind of set this up before. We're going to focus on some of these more than others, and we won't get into the real technical side of it. But what we're assuming is that expected value of our error term for different values of x was equal to kind of 0. That on average, we're making errors, right, in the same, like there's errors in either direction. On average, our error term using this line of best fit is 0. We're assuming that x and y, their distributions don't depend on each other. Once again, we're not going to dive into this too much. We'll kind of touch a little bit more on 4, probably on Tuesday's class. We also assume that we don't have these extremely crazy large outliers. So this would be like if I was estimating that wage data set and Elon Musk somehow got thrown in there, that assumption would be violated, right? We can't have extreme in it. How extreme is extreme? That's a topic we won't kind of dive into, but there's ways to test to see if you have some observations that would kind of violate that assumption. And then we can't have x always be the same value. This will be important for something we talk about on Tuesday, which is collinearity. Okay, so we'll kind of revisit point 4, something that we actually can test to see if that assumption is violated. Okay. So back to our kind of officers regression, we said, if I run this regression, what would the expected sign? If I have more police officers, what do you think should happen to the number of crimes? Well, I mean, anyone arguing for more police officers is expecting that they are a deterrent, right? Now, you could tell me maybe it's positive because if you have more police officers, you can identify more crimes, right? But there's likely things that we didn't include in our regression, like population, where if I left it out, police officers, the number of police officers will also be picking up the effect, not just of police officers, but also that variable population if I left it out. So here we can kind of think about, if I run that simple linear regression, notice what's the coefficient on police officers? Positive. When I hire more officers, I'm getting more crimes. Highly statistically significant. But that's because I left out this variable that would impact both my X and my Y variable. So the variables that we leave out of our regression will cause bias in our estimate if they are both correlated with X and Y. Right? So here we said population likely is a variable that impacts the number of police officers in the county and impacts the number of crimes, right? We just have more people, we're going to have more police officers being hired, and we're going to have just more crimes. So once we control for population, notice what has happened to that coefficient on the number of, well, it's still positive, right? But what's happened to the size? It's went from 33 to 14. It's been cut in half or more than half, right? So there was a bias in our coefficient estimate because we left out a variable that was both correlated with X and correlated with Y. If that's the case, when we run this simple linear regression without population, it picks up the effect not only of the number of police officers, but also some of that effect of just having more people or the population in that county.
And does this R squared show that these two variables combined account for that much of that?
Yeah, so I think I have slides in the future, but since you're asking the question, no, well, don't apologize. This is good. You're thinking about the next level of things, right? You beat me to it. That means that you actually are understanding it, right? So if I run a simple linear regression, now this one, kind of interesting. How much of the variation in the number of crimes is explained by the number of police officers? If I look at my R squared, almost 75%. So that one variable probably matters a lot, right? Now, if I include more variables, what should always happen? What's the worst case scenario? If I add variables in and they don't matter, what's the lowest amount R squared could change by? Yeah, 0. If I can explain 75% of the variation with the number of officers, if I add in variables that don't matter, but I also keep officers in there, what variation can I still explain? 75%, even if the other variables don't matter. Now, more than likely, I'm adding variables in because I think that they're going to help me cause or create better predictions. So as I add more variables in, as long as they have some effect or some correlation with Y, what should happen to my R squared? It should always go up. As I add in more variables, I can never see that R squared value go down. Okay. Now, adjusted R squared is a little bit different. I'm not sure if we'll quite get there today in the order in which I have things, because I want to spend some time in Stata. But the adjusted R squared might be a little bit different. But in terms of our R squared, when we add in more variables, it has to increase. Right. So here we can kind of think about going back to, which is a good question, but we're going to kind of return to this idea that when I leave out variables, I'm causing a bias in that estimate. So I thought of another easy one. So if I think about, I'm trying to predict a child's birth weight, and I have a dummy variable, whether or not the mother smoked while pregnant or not. This is an actual data set that has this, and I think they did it with like nicotine tests or something, which like are pretty short-lived. So that meant that when they went to the doctor, they knew they were going to get this test, and they still smoked relatively close to that time, which is alarming. If generally birth weights are a sign that the baby is healthy, right? If the mother is smoking, right, a dummy variable, the change in the units is going from 0 to 1. How would I interpret beta 1? If the mother smokes while pregnant compared to not, that beta 1 is the change in the predicted birth weight. If higher birth weights are better, what would we expect the sign of beta 1 to be? You smoke during pregnancy, and higher birth weights mean it's a healthier baby. It's likely that if you smoke during pregnancy, birth weights are going to go down. So we expect beta 1 to be negative. right? So let's assume I found it was negative. Okay, great. My intuition was right. I'm done. Well, not quite, right? Because let's think about what's an omitted variable here that might be correlated with the health of the baby, but also whether or not the mother smoked while pregnant. So this might be a little bit stereotypical, but if you look at the data, the statements I'm about to make are what word am I looking for? Verified. Like it shows that this actual correlation exists. So it has to be an omitted variable that's correlated with both our X and Y variable, correlated with whether the mother smoked during pregnancy and the birth weight of the child. So if income is left out of this regression, what do you think is likely true about individuals with lower income? Do you think they're more or less likely to smoke during pregnancy? More likely, right? So there's a correlation with the X variable. So some of that smoking variable is going to pick up the fact that income is negatively correlated with smoking during pregnancy, right? Because if I have more income, it's less like this. But also, if I have lower income values, what do you think is also true? Why might that be correlated with birth weights or health of the child? If I'm in a lower income bracket, what might I not have availability to? I might not be as likely to go to the doctor as much during my pregnancy. I don't have as much availability to high quality foods. All of these things would cause birth weight or health of the baby to go up. So even though I find a large negative effect here, it could be that the effect is even larger, right? But the true negative effect of smoking, maybe I'm picking up some of the fact that having lower income is actually worse for birth weights, right? So just because the sign lines up with our intuition, we still could have important omitted variables that are not just changing the sign, but the size of that estimate, right? So another example, I don't remember where I stole this from. Looks like I got the link or whatever down here. But if I look at across time, there is a strong positive correlation between organic food sales and autism. Do you think anyone is arguing that organic food sales are causing autism? I know that. I'm not aware of anyone making that argument. Why? Well, what do you think is probably correlated with both of these things being higher, right? Well, there's an increased focus on health, right? If there's more money being spent in the health sector, people are more likely to be trying to buy higher quality, more natural foods. But at the same time, we're trying to identify things in individuals that we weren't trying to do 50 years ago, right? So we now are identifying autism, whereas 50 years ago, this wasn't even something that doctors were really looking out for. So there's some of these outside factors that we haven't built in to this equation. Okay? So just because we have correlation between two variables, we would say we don't necessarily have causation, right? It might be because we're omitting some other important factors. So if this one goes over your head, maybe revisit this after we talk a little bit more about this today and on Tuesday. But I used to think that correlation implied causation. I took a statistics class, now I don't. Sounds like it helped. Well, maybe, right? Because maybe it wasn't that I took the statistics class that made me understand this. It was the fact that I was taking a statistics class because I was already in a group that was high, likely to have a higher education value, higher IQ, having a higher IQ. I was more likely to already understand this anyway, right? So we have these kind of omitted variables, and we want to think about how they might be impacting our coefficients. Because in my examples before, I was saying, oh, well, if I think that I have this omitted variable that matters, why don't I just throw it into my regression? Why might I not be able to do that? Maybe I don't have data on it, right? So I just listened to a presentation on the use of AI to predict stock market movements and comparing that to experts in the field's predictions, right? And so one of the omitted variables might be something like these experts, one thing they have that AI doesn't is some type of innate ability to their experience allows them to identify things that AI can't. Do I have data on that? No, right? I can't see what their internal thought process is. And so I might think about, even though I want to include variables, I might not have the data, okay? So we want to be able to put a sign to this bias. How can we do that? Stole this from a textbook. This is like the mathematics. We're not going to dive this deep into it. All we care about is the result, okay? So there is a mathematical proof for why this is the bias. But if I estimate beta 1 and I leave out this important variable x2. So that's what the regression equation should be, but I left out x2. I've omitted this variable. If I run just that simple linear regression, the estimate I see for beta 1 will include the true effect of that x1 variable, but also what would beta 2 represent? The effect that the omitted variable would have had on y. And then what is the covariance? That would have been the correlation between the variable I included x1 and this variable I omitted x2. Okay? So our bias, right, is going to be this added component here, right? It's how much our coefficient estimate was off from the true value. So we have beta 2. We can kind of think about, well, that would have been the effect if I had included x2 into my regression. This might not be obvious, but we actually looked at this already. We said another way of writing out a coefficient estimate. So I'll kind of put this in the context of what we've already talked about and then say, what does that thing look similar to? So if I was having a simple linear regression, we said that my estimate for beta 1 is actually the covariance between x and y divided by the variance of x. That was one thing that we kind of went through some state examples and actually showed this. Now, if I'm instead, part of that bias was the correlation between the variable we included and the variable that we omitted, right? How would I get this? Well, what's the only difference between these? I've got x1. Instead, y is x2. So this would represent my coefficient. We'll call this a hypothetical coefficient estimate. If I were trying to predict that omitted variable using the variable I included. So really, this is like the coefficient, my bias, we said was beta 2. The effect that would exist if we did include this omitted variable. Sometimes we can't because we don't have the data. But if we were able to include it, it would have been the effect that this second variable had on y, right? Or how it was correlated with y. The other part of that bias was essentially this hypothetical coefficient, which really just represents that correlation. So we can kind of think about this as my hypothetical coefficient, which simply represented that correlation between the variable I included and the variable I omitted. So we don't really have to worry about kind of the sign here because the sign of a variance is always what? So if I have a standard deviation, if I square any value, it's always positive, right? So I don't really have to worry about the sign of this. But here, the correlation of x1, the included, and x2, the omitted variable, could be positive or negative. The effect of x2, if I did include it, could be positive or negative as well. So the combination of these two things is going to determine what the size and what the sign of that bias is, right? So if I think about this bias, and here, if it just helps to think about, since we don't really have to worry about that denominator, I mean, I can write it in here, but we don't have to worry about its sign. If the covariance or the coefficient of the omitted variable were higher, what's going to happen to our bias? Either of these increase, our bias is going to do what? I'm using an equation. These are both in my numerator. If they're higher, my bias will be higher. Okay. Now, here's where we can start to think about these different combinations. So what is the sign of this bias? Okay. Well, if beta 2 was negative, and that correlation between the included and the omitted variable was positive, what's the sign of that bias? I would have a negative times a positive divided by a positive. The sign of my bias would be negative. All right? So those relationships of that omitted variable to the y variable and to the variable I included, that independent variable, dictates the sign of the bias. Okay? let's go through the other kind of examples. What if I had, well, here I should probably keep this consistent. Let's say I had this, right? So the effect of the omitted variable is still negative. Now the correlation is negative. Here I would have what? A negative times a negative over a positive. What would be true about this bias? Is it positive or negative? Negative times a negative is positive, divided by a positive value, it would be positive. And then you can think through the other kind of two combinations, right? If I have a omitted variable and it has a positive effect, and the correlation between the omitted and the included variable is positive, positive times a positive over a positive, my bias here, positive. And then if I have greater than 0, less than 0, positive times a negative over a positive, there my bias would be. And I don't know why I was writing bias with like kind of the coefficient estimate. It should be, you could put a B there. I just kind of typically for some reason, I kind of write it that way to think about, we're using those coefficients to determine the sign of that bias. So we can start to think through, if we have an omitted variable, how might it impact the estimate that we see? Okay, so I'll go through a thought experiment. I've got a couple different examples, but I'm going to use one that might be stereotypical, but I think that it's, once again, proven with data, and I think it's something that we can all maybe think through or have a relatable example. So let's say, oh, what do I want to do? So let's say I'm trying to predict college GPAs, and I want to use whether or not someone's a student athlete, just a dummy variable, okay? If I run this regression, I'm going to come up with an estimate for beta 1 that includes the true effect, but plus our bias. So the bias I'm going to think about existing is, what's an important omitted variable maybe I left off here? So let's say I didn't include this, right? It's what I left out. But if I had included SAT scores, right? What would the bias be that's caused here? So the bias would have been the effect of beta 2, or the, sorry, not the effect of beta 2, would have been the effect of SAT scores or beta 2 on GPAs, multiplied by the covariance between the variable I included and the variable I omitted. And then here I said, we don't usually worry about this because we know the sign, but the variance of that variable I included. So in this example, if I ran my simple linear regression, is my estimate going to be too high or too low? Okay. Well, what do you think the relationship of SAT scores are on predicted college GPAs? You score higher in the SAT, once you're in college, you likely perform better. Now, that's not everyone, right? But the kind of average correlation there would be positive value. Right? What do you think is probably true about the SAT scores of incoming student athletes compared to those who are not? If I'm thinking about admitting Mendoza to IU, do you think I'm a little bit more lenient on what his SAT score is, or less lenient? A little bit more, right? So if they're a student athlete, what would you expect the correlation of student athlete and SAT score to be? Student athletes likely have, on average, lower SAT scores, right? And it, economics, it makes sense, right? They're bringing something other than their academic performance to the university, so they have an added benefit, so they're likely to be a little bit lax on their academic standards because they're bringing in revenue from something else, right? So here, what would the sign of our bias be? Positive times a negative over a positive. We have a negative bias. The estimate that we're going to see includes the true estimate, but plus some negative effect. So our estimate is actually going to be too low, right? If we're assuming that beta 1 here is positive, right? If beta 1 was negative, we would actually see an estimate that is even a larger negative value, right? So the key here is we know that we're getting this added negative effect because of that omitted variable. Any questions on this idea before we keep moving here? Okay. All right. Where are we at on time? And what do I want to do? So I kind of have a summary of kind of those different combinations. I wrote them out for us, but here's kind of a nice summary slide of that. I went through basically this example, but we can show that this happens. So if I just run that regression of GPA on an athlete, what do I find? I find that I need to make sure I'm hitting this. You don't want to see my face. So we'll go back to the slides here, what I was talking about where we left off. Oh. Scroll all the way back down. Okay. So we were talking about that kind of relationship. If I just run that simple linear regression where I exclude SAT scores, I find a coefficient that is strongly negative and I reject, right? P-value of 0. If I include the SAT score, notice not only, so we said the sign of the bias was likely negative. Sure enough, instead of negative 0.28, what do I find? Only negative 0.05. So what was the size of my bias? So if I look at that simple linear regression, I then look at the regression where I included the omitted variable, the amount of that bias that was built into my original regression would be what? The difference between the initial coefficient I found and then the coefficient I found after I included the omitted variable. So here that's going to be about what? 0.23 or negative 0.23, right? So I can run the regression without and with that omitted variable, and the difference between those tells me the size of that bias. Okay. Now, this is also an important point to make. Even if it didn't change the size by very much, what can also be impacted by an omitted variable is the statistical significance. So the size of my coefficient change, but also what happens to its statistical significance. Can I reject the null now? No, whereas if I had that important omitted variable, I looked like I could reject it. So in fact, once I include SAT scores, now how would I interpret that student athlete variable? So it's a dummy variable. So a 1 unit change is going from the 0 to the 1 group. So being a student athlete compared to not would change my predicted GPA would lower it by 0.05 points, holding SAT score constant. So the idea now is two students with the exact same SAT score, but one of them is a student athlete, would I expect their GPA to be higher or lower? Lower. It is lower, but they have more time commitments. Maybe they can't study as much. But can I actually say that that effect is different from 0? No. Right. Now, this is also an important point to make. Just because I included one important omitted variable, there's likely a lot of other omitted variables as well that are still having a bias on both of these coefficient estimates. Okay. What if you were to add the time? Then I can hold that constant. I've eliminated that bias now. Right? So if I had like hours studied here, I've now removed that bias from the student athlete variable. But I might have a bias from, I don't know, what income bracket they came from, right? And that's going to give them more or less, access to the higher amount of, materials that might benefit them versus not, or whatever we think that relationship, or whatever we get data, what we estimate that relationship to be. So we've eliminated the bias of just omitting SAT. We still have bias from every other variable we've omitted. So what happens is I start to include more variables. I'm omitting more and more of that bias. If I'm eliminating that bias, what am I getting closer and closer to? Not just correlation, but I'm getting closer and closer to causation, right? Which is ultimately what we want to know. I want to know if I admit a student athlete, are they likely to perform better or worse than a non-athlete if I'm Kelly and worried about keeping my average GPA that I can put on all my flyers high, right? I might not want to admit as many student athletes to my programs. I shouldn't pick on Kelly, but so what's happened also as I add in more variables? What was my R squared when I just had student athlete? I was only explaining what percent of the variation in Y. 0.8%, right? I moved the decimal 2 places, so 0.8%. Once I include SAT score, that's a lot more of an important predictor. My R squared has went up to about 17-ish%, right? So, we're just kind of reiterating these questions that were asked earlier about thinking about R squared. So I went through this. If I think about what that bias is, I can actually figure out what the covariance of two variables are. As long as I have the data, I can figure out the variance, and I can figure out what that omitted variable's effect would have been if I have data on. So we can actually prove to ourselves that that equation for the bias will produce the correct bias. So when we looked at the actual data, we could see when I had the omitted variable excluded and when I actually included it, the difference between those coefficients was the bias. We can actually prove this to ourselves using data. So I'm going to go to that Stata file. Now, here's something we'll start doing. I'll be using some free data sets. So this very first command I have at the top of this do file, we'll start using this in class. It's called ssc install and then bqs. So this is a bunch of like data sets that exist. I believe it's in Stata somehow, or it's on a website that Stata can access. It then pulls in all these data sets. Here I put the clear command just because if you ever had a data set open, you need to clear it out, right? That was usually part of our use command when we opened up a data set. But when we're using these free ones, we have to first clear out any old data that I had open. And then I can use this bqs command. And there's a bunch of different free data sets we can access. So the one that I'm going to access is called GPA2. So now it has all this. I look at my data. I've got this data set, right? Nice and free, a little bit different than how I would usually have to give you the .dta file and have you open it. You can just access it from kind of the built-in behind-the-scenes stuff on Stata. Okay. So I wanted to, before we get to this omitted variable, I wanted to point something else out that up to this point, we've only really done by hand. But I wanted to show you if you're using AI or if you're Googling, you might have already come across this. Okay? So if I run a regression, instead of doing all the work by hand to make the predictions that we started class with, where I said, okay, here's a hypothetical coefficient, I'd multiply it by the hypothetical X values to come up with my prediction. So if I run a regression, and here I just did college GPA on SAT scores. Okay. So I know the effect of a 1 unit change in SAT, 1 point higher on the SAT, increases predicted college GPA by 0.0019. Pretty small effect, right? But let's say I'm like, well, yeah, 1 point higher on the SAT is a really small increase. What's the effect of maybe scoring 50 points higher? Well, if I know the effect of 1 point, the effect of 50 would just be that coefficient times 50. So when I run a regression, instead of having to type in the value or write this down or do the math on a calculator, I can access that estimate for the coefficient by after the regression using this underscore B, essentially that coefficient estimate, right? You can't type Greek, so it's using alphanumeric instead of beta, it's B. And then in these brackets, you'll put what you want the coefficient, what variable you want the coefficient of. So this is going to take that coefficient of SAT. It's going to use that value. Here's another nice thing. You don't have to round, right? It's using the value out to whatever decimal Stata has stored behind the scenes. I then multiply it by whatever hypothetical X value I want to make a prediction for, right? And this would give me, and I can use just the display command, right? Because I could create a new variable, but generally we don't want to do that just because it starts to like add a bunch of stuff to my data set that I really don't need. I just wanted that one value, right? I don't need to make that for every observation. So if you want to kind of do math using those coefficient estimates, you can just use this display command and it'll put the value in there for you. So if this was like a question on the next problem set, I could then say, okay, here's my command. It displayed the value of, 0.09655 to me. Okay. Now you could also use another command in here, which is to predict GPA. If I run a regression and then I use this word predict, I can then create a variable that would show me not the actual GPA for every person in my data set, but the predicted GPA using that regression output. So if I put in this word predict, what it should do is for every single observation, take that intercept coefficient, add to it the SAT coefficient times that person in the data set's SAT. That's what that predict command will do. To verify that's what it's doing, I created a variable that I said predict GPA manual, where I took the saved coefficient on my intercept, or what Stata calls my constant. Now here, you gotta be a little bit careful. There's an underscore in front of constant. The kind of regression output reminds you of that, but it's not just CONS, it's underscore CONS. Right? So the variable I'm creating here, I'm kind of doing it manually. That predict command will do this all behind the scenes. If I'm lying to you, when I have the predicted GPA variable and the predicted GPA manual, those wouldn't be the same. Hopefully I'm not lying to you. So when I do this, I look at my data. Sure enough, I get my predicted GPA using that predict command. Or if I do it manually, kind of using those saved coefficients, I'm getting the same predicted values for Y. Okay? So what it's making those predictions based off of are those coefficient estimates. And then in the data, the hypothetical, because we have a simple linear regression, simply looking at that X value of the SAT score for the individual to make that prediction. Okay. Any questions on that idea before we keep moving here? Okay. Man, I wish we didn't get caught up because we'd have enough time to do all of this. I'll show you this very quickly. Well, yeah, we'll start here. If we have time, we'll get back to this. If not, I can use this on Tuesday to kind of revisit the idea of homo and heteroscedasticity. It wouldn't be anything kind of expected of you on the upcoming problem set, which I should get that third problem set, and you don't have to start working on it, but I'll get it posted tomorrow. So if you want to, after this problem set, start working on kind of the early questions, you can kind of get ahead on that. So I'm going to clear out my data set, just reuse that GPA data just to kind of clear everything out. I'm going to run this regression of college GPA on athlete like we just did, right? Or the one I showed you in the slides. So I get that negative 0.28. So what should that include? It should include the bias of leaving out that important omitted variable of SAT score. Okay? So if I'm leaving out that important variable of SAT score, what should my bias be? The effect, if I had included it, beta 2, and then the covariance of that omitted variable SAT with the included variable of athlete divided by the variance of athlete. So what I can do is say, okay, look, let's say I look at the correlation between athlete and SAT score, okay? That correlation is negative 5.45, so I now can plug that value in. The cross, when I do that correlation, what's the correlation of a variable with itself? That would simply represent the variance, right? So the variance of athlete, that variable I did include, was 0.00 or 0.045, rounded to the kind of second or third decimal. And then if I did include that omitted variable, what would the effect have been on Y? Well, that value was what? Negative, or not, it's not negative, sorry. We're looking at SAT, so 0.0019 or 0.0019. So I've plugged in now beta 2 is 0.0019. I've got the covariance of those two variables. I have the variance of the variable I included. That should be, if I kind of do this and I could create a new variable. So let's say I even wanted to create that variable. And I could use display if I don't want to add an additional variable into my data set. So I calculate what that bias is. Oh, what do I didn't like that? Oh, because I put kind of what it should be. So if I then generate that variable, I get the bias was negative 0.23. Well, remember, another way that we could look at that was if I run the regression without the omitted variable and then run it with, we said the difference between those two coefficient estimates should be the size of the bias, which sure enough is negative 0.23. Right? So if we have the data, we can always kind of do that manual calculation of the bias. But really, if we have the data, it's pretty much as simple as like just looking at the difference in those coefficients of if I do include or if I omit the variable. All right. So this is just kind of proof that that equation works. It's giving us the same value. Okay. Kind of save time for this. We might revisit this on Tuesday's class. So we'll kind of come down here. If we run that same regression, another thing I wanted to point out since we were just talking about it, is I don't just have to make predictions from a simple linear regression. I can do the same thing with a multiple linear regression. So here, if I run this regression where I've included now both athlete, student athlete, and SAT score, if I want to predict the college GPA of a non-student athlete with someone who has a 1200 SAT score, right? All I would do is use this kind of underscore B. I can look at the coefficient of the intercept, add in the coefficient on athlete times whether or not they're an athlete. So this person, they weren't. I then look at the coefficient of the SAT score, multiply that by the hypothetical value for that person's SAT score. It's going to show me that value. So what's the only difference between these two predictions that I'm looking at? They have the same SAT score, so I'm holding it constant, but one of them is a non-student athlete, one of them is a student athlete. So what should the difference in those predictions simply be? That coefficient on student athlete, which we have here, is what? Negative 0.05. So hopefully, when I run this command, if I take the difference between these two values, sure enough, it's right around negative 0.05. And then kind of similar to how I did before, I can also make predictions using that predict command or doing it manually for every single observation. It's just I can include more than one variable. I can include multiple variables here as well. And the kind of difference is there, I can take the coefficient. I just have to put whatever the variable name is of the coefficient that I want. Okay, so just a little bit more work there. Okay. Another way, just as we're thinking about things, and some of you have like approached me about thinking about data, and if you were to use Stata or even R, if you ever end up working with a professor or doing a little bit of research or working with data sets, if I create this predict command using the predict built-in command, or I create it manually, right? So I'm going to do both of those. I can look at the data and say, okay, yeah, it looks like it's kind of the same value. But in certain situations, maybe I made a mistake and it's off by a little bit. So a really good way to check if you're doing things or coding things the right way, if you know two things should be equal to each other, like maybe I created this manual and let's say I don't know, let's say I forgot the constant, okay? So just to kind of make this point, I'm going to drop this variable real quick. Right? I'm then going to recreate it, and I forgot the constant. Okay. So instead of just looking at the data, maybe the constant was like really small. If it was like 0.00001, I might not notice my predictions are off. If I create a variable, I generally call it like check to say, okay, the variable I created using the built-in predict command, it should be the same or equal to the variable I created trying to make those predictions manually, right? We looked at that before with a simple linear regression. I'm telling you, you could do the same thing, but with multiple linear regression, you just have to add in multiple variables. I forgot the constant, so what should be true? These aren't the same. So if I create this check variable, I then put tab check. Because I know I made a mistake, every single time, will this statement be true? No, right? It's going to be off. I made a mistake. So if I kind of run this, oh, sure enough, I must have made a mistake somewhere. Right? So I then say, okay, I must have created this variable incorrectly, so I'm going to drop it. Oh, sure as shit. I forgot to include the constant. Oh, what did I type in wrong here? Sorry. Hit another button. Right? So now I say, okay, now I think I've got it correct. And actually, I forgot B there, right? So now I'm going to create that same variable. I have to get rid of that check variable because I created it with the wrong value first. Now, when I recreate it, hopefully when I hit tab, if this does give me the exact same value, now the only values I should have in that check variable are all ones. So it's a good way to make sure I didn't make a mistake. Okay. So just trying to kind of show you some things along the way that maybe not necessarily like applies to specific questions, right? But if you start working with data yourself, this is a good way to make sure you didn't make a coding error somewhere. If I think the predict command is doing the exact same thing as what I'm doing manually, I can always make sure. Okay. So I think next class, I'll revisit this predict command and we'll kind of look at homo versus heteroscedasticity. We'll then kind of move on to thinking about our R squared again and our adjusted R squared. But before we get out of here today, I also have this quiz. And since everybody's here, I think I put it in there as, what did I do? We'll see. I think I put in there 1247, 12.47. We'll see if that's the case. Yeah, 12.47 is the access code. So I'm going to go ahead. So 12.47 for that in-class quiz 4. So we're now going to access this. We'll actually talk through this one together. There's one question. Hopefully this will be an easy one today. Okay. So if I'm thinking about here, if I have this regression equation where I'm looking at exam scores, we can see the answer here. So this, hopefully everyone gets this right, but let's talk through it, right? So I'm trying to predict upcoming. So I gave B251 exam this morning, right? Maybe I'm wanting to predict, I could be the number of classes or the number of help sessions that are available to them, right? I actually have this data. I've looked at this before. Maybe we'll use it later on in the semester. Obviously, I won't have any student names with it, but I have the actual values. So if I run this regression, I'm going to have the true effect of the number of help sessions they attended, but I'm also going to have the bias. And here I'm going to think about the bias that would exist between the number of help sessions they attended and something I don't have data on, which is their internal drive, right? And this would be the variance of the number of sessions here, right? So this is where if we don't have data, yes, we can't come up with specific values for the bias, but we can think about if my bias is going to be negative or positive, or my estimate's going to be too high or too low. So what do we think? If I did somehow have data on what someone's internal drive was, right? What do you think that effect would be on your exam scores? Positive. What do you think? The number of help sessions someone attends, do you think that's positively or negatively correlated with their internal drive? Positive. So what do you think I'm going to end up with? A bias that is positive or an estimate that is too high, right? So I could think about, oh yeah, it's going to look like when I run this data, attending my help sessions are really important, right? They learn everything from me. Now, it's picking up a huge positive bias from the people that attend those help sessions are also already have some internal drive and are likely studying more things like that. Okay? So we can start to put signs to bias even when we don't have that data. I was actually talking to a student who stopped in the other day, and we were talking through kind of this idea of college basketball and transfers and increasing your quality. If I have more transfers, I'm likely increasing the quality of my team, right? I'm paying these players to come play for me. So maybe it looks like the number of transfers are actually having a positive effect on my team's performance. But if I'm omitting an important factor, which is something like there is a measurement I don't have in my data, which is the cohesion of players. And when they play with each other for more years, that actually would have a positive effect on the team's performance. Then if I omit that, I don't have data on it, looking at the number of transfers might have a positive or negative bias built into it. I'm not actually getting the causal effect of bringing in more transfers to whatever my team is, the football team, basketball team, because I'm omitting this important thing, which is that likely correlated with the number of transfers and performance, which is how long have these players played with each other. I know that if their transfers coming in for 1 year, that cohesion measure would be low. I know they're correlated. So we can start to think through these different examples, start to think about the sign of our bias. Problem set 2 and the quiz are due tomorrow. I put up some additional office hours I was going to have tomorrow, and lo and behold, something came up, so they're going to change. I will put an announcement up. Instead of, I think I had like 8 to 10 or something in the morning, I'm actually going to be in my office from 12 to 2 tomorrow. So if you do have some last minute questions and want to stop by, I should be available from 12 to 2 tomorrow. I'll put up a Canvas announcement that kind of changes that. Other than that, sorry for the technical glitch. I'll get those videos kind of spliced together and posted later today. And have a fun, safe weekend. I will see you on Tuesday.